Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, this is our module number 5, linear regression machine learning approach. In module 3, if you remember, we looked at the exact same model, the linear regression models, but it was econometric approach. But here in module 5, now that we have covered the fundamentals of machine learning and we know how the machines actually learn, it is time to look into our very first simple machine learning model, which is linear regression. I want you to pay very good attention. This is exactly the same model. The setup is the same, the way that we write it down, everything is the same. But why do we call a linear regression model sometimes econometric model, sometimes machine learning model? So what's the difference? So hopefully by the end of this video, you have a good understanding of why do we call linear regression sometimes econometric, sometimes machine learning. So let's dig into that. Okay, so as I said, this is our very first machine learning model, which is linear regression. Later on, we're going to look into the more complex models in the semester. Okay, we're going to do this in two parts. In part one, we start with the very simple or multiple linear regression model, which is basically a model like this. We can say y is equal to, let's use machine learning language, w is w0 plus w1 x1 plus w2 x2, and etc., right? Of course, we can go ahead and add an error term, epsilon or u, right? So this is a very simple linear regression or multiple linear regression model. And then in the second part, we are going to do polynomial regression model, which is a special case of that linear regression model. So we can have w0 plus w1 x1 plus w2 x1 to the power of 2, w3 x2, and etc., right? And again, plus some noise. And then if you look at these two models, you may say, okay, this is exactly the same as econometric, so why do we call it machine learning now? Just at a very high level, pay attention to the complexity of the model and the purpose. What are we doing, right? So yes, if I want to do something like this, it really doesn't matter if I want to call it econometric or machine learning, but in econometric, the focus is on interpreting these coefficients, right? I want to see if this number is a statistically significant, if this number is a statistically significant at some percentage, right? Significance level. And then if that's the case, in order to basically answer that question, we have to make some assumptions. Remember from module 3, classical linear model assumptions. And if those assumptions are not violated, then we can say, yes, the story is there, these w's of significance, and etc., right? And then we don't focus that much on the predictability part, right? So that's why we usually keep these number of let's say features in the model relatively small, right? So let's say I have k of these, so wk, xk, k of these variables, and then usually k, again, in order to keep it interpretable, k is relatively or usually small, right? And however, in machine learning, because we want to make the model more flexible, or at least we want to control for everything which is around us, right? We can literally increase those number of k's and then say, hey, we have more features, maybe thousands of features. But as soon as we do something like that, many of these things are going to become less significant because again, in the econometric part, we talk about those things. But I don't know, maybe we can get a bit better prediction power. So in machine learning, the focus is on prediction. So again, when it comes to the simple linear regression model or multiple linear regression model, it really doesn't matter what you want to call it. You can call it econometric, you can call it machine learning, but just remember the purpose is kind of different. However, when it comes to polynomial regression model, then this is the part that really these things get separated, econometric approach versus machine learning approach, right? Because in econometric approach, again, as I said, the focus is on interpretability. I want to say, what is the story here? So what do they need? What do these numbers tell me? However, and then usually we don't make it super complex, right? So for example, if it is an econometric approach, I say, you know what, let's go to the power of, I don't know, probably we have W4, x2 to the power of 2, and maybe let's stop here, right? Maybe W5, x1 to the power of 3. Because if I go further, then interpretability of this model is going to become harder and harder. Because remember, how do we interpret these coefficients? We have to take derivative and then plug some numbers and then talk about the partial effect, right? If I have x to the power of 10, x to the power of 9, then it's really hard to interpret. So that's why usually in the econometric approach, we stop here. We say, okay, you know what, let's keep this polynomial degree small. Let's keep the number of, let's say, variables relatively smaller. But in machine learning, we say, no, there is no limit. Let's make it as complex as possible. So let's say in machine learning approach, I'm going to go to the x to the power of 10, x to the power of 11, whatever, w15. Okay, so then because there I'm less concerned with the interpretability thing, I want to focus more on the predictability. So that's why I'm going to make this model as flexible as possible. But of course, that comes with a caveat too. So here in the machine learning approach, we're going to learn what are those caveats, how we can play around with the bias variance trade-off and things like that. So let's talk about these topics. Here's a roadmap for different machine learning algorithms and models that I'm planning to cover for this conceptual crash course. Later on, I may add some other models if I see there is enough demand for that. Okay, so let's start with our supervised algorithm. And the first model is going to be a regression model. We start with the very basic one, linear regression model. Part 1, linear regression. Okay, so what are the linear models? The linear model is an important example of parametric model. If you remember from our previous parts, we talked about what is parametric versus non-parametric. Parametric models were the ones that we are not imposing any functional form, any restrictions to the model, right? So for example, in simple linear regression, we had something like this, y is equal to beta 0 plus beta 1. This is in econometric language. x1 plus beta 2, x2, and etc. Plus some noise or unobserved factors, right? So we are imposing some linear structure to the model because we are imposing that f of x to the model. We call it its parametric. Okay. So in linear regression model, we have a collection of labeled example because as we said earlier, it's supervised, right? So we need to provide both x and y's, inputs and output to the model. And n is the size of the collection, basically size of the our sample size. And x is a d-dimensional feature vector. So for example, if you're trying to predict what is wage, and the features can be experience, education, gender, age, and etc., right? It's a d-dimensional vector, and y is our real valued target variable. Because remember, we were talking about what's the difference between regression versus classification. If the target variable is real valued, is continuous, we call it regression. Now let's rewrite this simple linear regression model in its machine learning format, machine learning terminology. So in machine learning, we show the betas, or with W, we call them weights, and this B that we used to call it intercept in econometrics, in machine learning, we tend to call it bias, okay, the constant or the bias term. And we can summarize this function as f of W and B. This is the thing that the machine is expected to learn, right? The machine is expected to come up with an estimated version of this pattern in the data, and it's going to do that by solving for the weights of the features and the bias term. Okay, and so f of W and B is a linear combination of features and parameterized by W and B. Remember, these models are called linear because they are linear in parameters. So as long as the model is linear in parameters, so we have, for example, W1 x1 plus W2 x2 and etc. As long as the model is linear in parameters, we call it a linear model. So for example, if I have here to the power of 2, or if I have interaction between x2 and x3, these are still perfectly linear model because the model is linear in parameters. All right, our W, the weight matrix, is going to be a d-dimensional vector of parameters, and B is a real number. All right, our linear model is going to be specified with d+1 parameters. Why? Because remember, this weight matrix is going to be d-dimensional because we have d features, and we need to estimate also this bias term as well. So the model needs to estimate d+1 parameters. Okay. We estimate the parameters W stars and B star by fitting the model to train data. So imagine this is the entire data set. As we said earlier, we're going to discuss, split it into, let's say, 80% train set and 20% test set. And the model is going to learn the parameters of the model, namely W stars and B star, using the train set. Okay. then although it is almost never correct, but a linear model often serves as a simple and interpretable approximation of the unknown true f of x, right? So remember, guys, at the end of the day, we are trying to estimate this true relationship in the data, but we know that it's unobservable. And linear regression model is going to be a very simple model, and most importantly, it is interpretable, because you can perfectly interpret the weights. These are the loadings or weights of the features, right? So for example, if the weight for feature 1 is W1, we can perfectly interpret this one. All right. So one of the big advantages of linear models, linear regression models, is that it's simple and interpretable. And it may seem overly simplistic, but remember, linear regression is extremely useful, both conceptually and practically. So this is one of our simplest machine learning models that has huge application because of its interpretability. Because remember, sometimes even in machine learning, you're still interested in being able to interpret things. So linear regression models rarely overfit. So what do we mean by that? So look at this example. So here we have, imagine this is the true relationship are these blue curve, right? So the blue curve is the true relationship. If you use a linear regression model, a linear model with a linear fit, right? So this is linear fit, right? This orange line is our linear fit. In this example, it is obvious that it's not going to overfit at all, right? But if the model is linear, but the fit is nonlinear, so this is nonlinear fit. Again, in this example, as we can see, it's doing a perfect job and it's capturing the true relationship in the data without specifically overfitting the data. And then the third one, the model can be linear, but the fit can be nonlinear as well. So this is, again, another, let's call it complex nonlinear fit. In this example, this orange curve is it's capturing noise. It's not capturing the true relationship in the data. Basically, it's memorizing from the train set. And obviously, it's overfitting here. So linear regression models, guys, in this example, all of them are linear. But because we want to keep this linear regression model mostly interpretable, we are not going to make it super complex like what we have here. So in general, when we talk about linear regression models, at most we have the quadratic version of the features in the model, and that's it. And we keep it very interpretable. And for that reason, if we stick to a linear fit or a nonlinear fit like this, it is going to rarely overfit our data. Now let's talk about the fact that in linear regression models, how do the machines learn the pattern, learn the code, and basically find the W stars and B stars? So here is our optimization problem for the linear regression model. We are basically minimizing the mean squared error over some parameters of the model, namely W's and B, right? So this is the definition of mean squared error. If you're saying this is residuals error y minus y hat, and we square them and we take the average. So this is our mean squared error. And if we can replace this y hat that the machine is going to estimate by this function f of w and b xi, right? So this is what we call the objective function, or in general loss function or cost function, right? So in all those machine learning models that I show you in the first page, we are going to introduce a specific loss function. Not necessarily all of the models, but most of the models have a loss function. And the goal for the computer is using one of those solvers that we talked about earlier to figure out what are the optimal values of parameters, right? In this example, our loss function is a squared error loss. So here I have a question for you. Why we are using quadratic loss function? Why not using absolute value or cube? So why we don't do something like this? So for example, absolute value of y minus y hat, summation, or summation of y minus y to the power of 3, and etc. So what do you think? Yeah, as you may have guessed, the answer is it is more convenient to work with a quadratic loss function. Why? Because it is well behaved. And by well behaved, I mean it's going to be continuous and there's derivative at every single point. So it's well behaved. And also, there exists a closed form solution. We know that from our econometric, I assume that you have a background in econometrics, and from the econometrics course, we know that there's a closed form solution to this optimization, and we call that engine OLS, right? Ordinary least square. And we could calculate the coefficients of beta hat using this formula, x prime x inverse x prime y, right? So here we are calculating the weights. We just renamed the betas by weights. And now we can either use OLS or use gradient descent. So maybe here's a difference between what we do in econometrics and what we do in machine learning. So in econometrics, we always use OLS or some other engines to estimate the parameters. In machine learning, we can use gradient descent as one of the solvers to solve for the parameters W star and B star, right? And because this loss function is very well behaved, you must always get the same answer. So it really doesn't matter if you use OLS or if you use gradient descent. All right, so now that the model has been trained using the train set, and the machine was able to find the W stars and B star, either using OLS or gradient descent, it is time to make some estimation in the test set, right? It is time to calculate for those Y hats, make some predictions. And with those predictions, we can compare the model performance by using some evaluation metrics. So one of the most common evaluation metrics that we use for regression is R-square. And it is defined as the explained part, sum of square of explained divided by sum of square of total. And I assume that you have some basic backgrounds in econometrics, so I'm not going to talk about the details of these formulas. And I assume that everybody here is familiar with the concept of R-square. But we know that there's a caveat with this formula for R-square, right? Because as long as, so let's say this is my Y variable, the target variable, and we're regressing it on X1, X2, and etc., right? The caveat is that we know as long as these variables that you're adding to the model, as long as they're relevant, basically there's correlation between them and Y, your R-square is going to decrease no matter what. So this is a problem, right? Because you don't want to keep some random variables on the right-hand side and get a better R-square. So what should we do? We're going to use the adjusted version of R-square. So we call it adjusted R-square, and we're going to do something like this. We say, okay, if K increase, then R-square is going to also increase. Then we have to look at the net effect of that increase in K, right? So if K increase, this whole thing is going to decrease, right? Because when R-square increase, this whole thing decrease. And the denominator is going to, on the right-hand side, is going to decrease, so the whole thing is going to increase. At the end of the day, we have to compare this effect with this effect, right? Let me use other colors. If K increase and the 1 minus R-square decrease a lot compared to a slight increase here, then what will happen? The adjusted R-square is going to increase. So adding that extra variable was beneficial. So we're going to go ahead and add that variable. However, if you add a variable and the R-square, let's say, decrease, but this right-hand side increase more, then your adjusted R-square is going to decrease. So it was not beneficial to add that right-hand side variable. So this is the adjusted version of our evaluation metrics R-square. What other metrics do we use in regression? So the other metrics, the one that are commonly used are mean absolute error, basically looking at errors, the absolute version, and take the average, mean absolute error, mean squared error. So this is basically, we talked about it in our loss function, and also the root mean squared error. So this is, we take the square root because the unit of root mean squared error is the same as the unit of the target variable. Okay. Then we can think of the adjusted version because we have the same problem here. Here we know that if I add some random explanatory variable, some random features to the model, let's say xk, then RMSE is going to basically is going to decrease no matter what. because when we add explanatory variables, more explanatory variables, the errors are going to decrease, right? So this thing is going to decrease. All right, so what are the adjusted version for the RMSE or MSE? Well, we can use something called AIC and BIC. So AIC stands for Akaike Information Criteria, and BIC stands for Bayesian Information Criteria. The idea of these two statistics or metrics are pretty much the same. We are basically looking at the function of k. K is the number of explanatory variables or number of features, minus a function of likelihood, right? So again, a function of k minus a function of likelihood. So what is likelihood function? We show it with L hat. And later on in logistic regression, I'm going to talk about the details of likelihood function. But for now, just think about it like this. What is the probability that the true data, the true observations are coming from the model that you're specifying, right? So what is the probability that given the values for parameters? So we say that, okay, given the values for W and B, what is the probability that the data is coming from this model, let's say this linear regression model, right? So most probably it is obvious that you want to maximize that probability, right? So if you want to maximize that probability, you would better to minimize the negative of that probability, right? So in general, we always want to minimize the AIC. When you compare different models, you will pick the model with the smaller AIC. Now let's see how it's going to adjust for the fact that when you add more explanatory variables, it has to penalize that statistic somehow. So here, as I said, the idea is simple. It's going to have, look at that. If k increase, this part is going to increase, right? So both for AIC and DIC and BIC, right? So we know that if you want to minimize this thing, so we have to keep it in balance, right? Because this thing is going to increase, yes, and yes, the probability of likelihood is going to also increase, and so the negative version is going to decrease, right? So again, as we discussed it in adjusted R-square, here for AIC and BIC, there's a trade-off between the two, right? So we have to see which effect dominates. And that's how AIC and BIC are penalizing adding k, adding more explanatory variables to the model. All right, but I want to talk about something that we do in machine learning. Now, if you notice, in machine learning, we rarely use these metrics, adjusted R-square, AIC, BIC, and etc. And there is a reason for that. And the reason that we use these metrics, these adjusted versions in econometric is that usually in econometrics we use a train set and we look at the performance of the model in train set as well. Because in econometrics, we are mostly interested in being able to tell a story. We are mostly interested in the interpretability of the model. What are the coefficients? Are the coefficients significant or not? And etc. etc. Right? Yes, if it is time series, we look at out of sample versus in sample. But in general, in econometrics, we have one sample and we report the performance metric in that one sample. So for that reason, we have to work with the adjusted versions of the metrics. However, in machine learning, we have train set and test set, right? So here is our train set. Here is our test set. And at the end of the day, we are comparing the models by looking at their performance metrics in the test set. Or, now that you know what is the idea of cross-validation, it is better to use report the performance metrics in the cross-validation set, right? Which is built on top of the train set. So for example, so what do I mean? I say that in machine learning, when you're calculating the RMSE, you report the RMSE of the cross-validation set or cross-validation version, or you report the RMSE in the test set. In either case, this is going to automatically control for the factor that we are not overfitting. Because we know that if you overfit the data, the RMSE in the test set or the RMSE of the cross-validated version is going to explode, right? So it's as if using the performance metrics in the test set or the cross-validated version is going to automatically do that adjustment for us. So I don't need to report the adjusted R-square in the test set. I don't need to report the AIC in the test set. In regression, when I do RMSE in the test set or cross-validation version, it is automatically controlling for that fact. And it's automatically help us to avoid overfitting using our linear regression model. Part 2, polynomial regression. Now, polynomial models are basically supervised machine learning algorithm and are an extension to our linear regression model. So we put them in the same category, linear/polynomial regression models. Now let's see what is polynomial regression model. The polynomial regression model is a special case of multiple linear regression model. Let's see how we can construct that. Do you remember from our linear regression model, we had f of w and b. It was a function of x, right? So we said b, our bias term, plus weight 1 multiply feature 1 plus weight 2 multiply feature 2, and etc. Right? So here, if we assume that, okay, feature 1 is x, feature 2 is x squared, feature 3 is x to the power of 3, and etc., then this is basically what we call polynomial regression model, right? So for example, you can think of one of those features. Imagine we have education, right? If I add education to the power of 2 to the model, to the power of 3, 4, and etc., this is our polynomial regression model. So what is really important in polynomial regression models is that we are not really interested in the coefficients themselves, right? I.e., we are not interested in interpreting this model, because what if I have, let's say, education to the power of 5, to the power of 6, to the power of 10? There is basically no way or no point to interpret that coefficient, right? And in general, this is a machine learning model that's mostly used for predictions rather than the interpretation, right? And let's see what are the variables here. So W is our d-dimensional vector of parameters. So we are going to have basically d parameters, W1, W2 up until WD. And B is our bias term, which is a real number. And D here is a new thing, right? We didn't see D in our linear regression model. And that's actually what we call hyperparameter. Hyperparameter. So this model is going to have both parameters, W's and B, and hyperparameter. And it's also, as we discussed it earlier in the linear regression model, it's also a parametric model. Why? Because we're imposing a functional form to the data, right? To the model. So the functional form is something like this: wx plus w2x2 plus w3x cubed, and etc. So we are imposing this functional form. So for that reason, it's going to be a parametric model, which has both parameters and one hyperparameter, which is d. D is the polynomial degree of the model, and we call it hyperparameter. So what is the difference between parameters and hyperparameters? I think in earlier videos I talked about it, but let me quickly remind you. So when you have a test set and train set, imagine this is a data, this is your train set, and this is your test set, right? You're going to use a train set, the machine is going to use a train set to learn the pattern in the data, to train the model. By training the model, the machine is going to learn the parameters, W star and B star. However, before even training the model, we have to start with some pre-specified value for our hyperparameter. So let's say D. D1. D1 is going to be, I don't know, one number. Let's say, we are going to make an example that the number of polynomial degree, let's say D is equal to 5, right? And then we start training the model with that. So we're going to figure out 5 W stars and 1 B star, right? And then after that, when the model is trained based on some pre-specified value for hyperparameters, we're going to make predictions in the test set. We call it y hat. And after that, we're going to use the performance metrics to report the numbers in the test set, right? So let's say R score in the test set, RMSE in the test set. So I want you to be aware that this D at the very initial run is going to be pre-specified, but afterward, we're going to optimize that D itself by using cross-validation. Okay, so make sure that you watch the videos when I talk about cross-validation and tuning hyperparameters. All right. So what is the optimization problem for a polynomial regression model? The optimization problem is going to be exactly the same as for the problem in the linear regression model, right? So basically we are minimizing the mean squared error over W's and B, right? So basically we are minimizing the errors, square them, and then take the average. And this function is going to be exactly the same as the loss function in linear regression model. So what does it mean? It means that it's going to be well behaved. It is continuous, differentiable at any point, and we can use either OLS or simply our gradient descent. So the idea is that for this optimization problem, there's also a closed form solution, So we don't need to necessarily use some sort of numerical optimizers like gradient descent or stochastic gradient descent. But if you want, you can. So the solution to this optimization problem is going to be W stars and B star. And now that we have the W star and B star, you can specify your f hat of x and make predictions based on that. So we are ready to make predictions. So on the right, we are looking at the data sets versus polynomial regression model fits, right? So imagine these purple dots are the raw data, and now we're going to use three different models to fit the model to the data, right? All right, so the first one is when the value of hyperparameter is equal to 3. So when d is equal to 3, we're talking about this red curve, right? As you can see, it is capturing the relatively upward sloping relationship in the dots in the data, but it's kind of missing out let's say the seasonality in the data, the going ups and downs in the data, right? So maybe we need to increase the polynomial degree. So if we increase the polynomial degree to 5, we get something like this. So here d is equal to 5. So 5 is going to be more flexible. As you increase the degree of polynomial, you're making the model more flexible, right? And then you can say, okay, let's increase it to 9. If we increase the polynomial degree to 9, it's going to be a lot more flexible. In this example, it's not a bad idea to make the model more flexible because it's capturing let's say, the true relationship in the data. However, one of the caveats of polynomial regression model is that it can overfit. It can overfit, and then we're going to talk about how to avoid those overfitting. So how do we avoid overfitting in polynomial models? We're going to do that by tuning the hyperparameter d in the model. Remember, d was the hyperparameter and was the degree of polynomial, right? Let's look at a very simple example. Imagine these dots are the true data. So the true data are basically the blue dots that we see. And the blue curve here is going to be the true relationship. I call it true f of x. This is the true relationship in the data. And remember, guys, this true relationship is unobservable. And in machine learning, we are trying to estimate, get as close as possible to this unobserved relationship, right? We're going to estimate that function. And now, let's plot RMSE. This is the performance metric that we used in linear regression. So we're going to use the same performance metric in the polynomial regression, because basically we're looking at regression analysis, right? Y minus y hat. So we can talk about mean squared or RMSE, the root mean squared error, right? So if I plot the RMSE in the test set versus the model complexity, so let's call this one model complexity, which is a function of d, right? So let's say here is simply d, right? If d is equal to 1, the model is very simple. If d is equal to a large number, let's say 10, the model is more complex, right? So it's simple. As we go from left to right, the model is going to become more complex. So this is a simple model. All right, now let's try to, roughly speaking, visualize this plot, right? So imagine we start from here when d is equal to 1. So if d is equal to 1, look at this line. So we're going to get a linear regression, and the fit is also line because it's to the polynomial to the power of 1. And as you can see, well, the model is this model with polynomial degree 1 is not capturing the true relationship in the data. We know that the true relationship is curvature, but this is some simple line. So the RMSE in the test set is going to be large, right? So let's say this is the RMSE. So this is for d is equal to 1. Let's say here d is equal to 3 and here d is equal to, I don't know, maybe 9, right? And we have here d is equal to 2, d is equal to 3, and maybe d is equal to 9 is here. Okay. And as we increase the degree of polynomial, then the model is going to become more flexible, more complex. It's going to be able to fit the data better. So if the model fit the data better, the errors are going to reduce. If the error reduce, the MSE is going to get smaller. If the MSE decrease, the RMSE is going to decrease. So as we can see, when we make the model more complex, the RMSE is going to decrease, right? And as we make the model even more complex, in this specific example, it seems that the RMSE is also decreasing. So when d is equal to 3, we have a very relatively good fit to the model, right? But as we increase the complexity of the model, it comes at a cost, because let's look at this exaggerated version. So here, this is our model, right? The fit is very nonlinear. And we know that, yes, maybe it's performing a good job. Actually, here it's doing a perfect job in the train set. But remember, this is machine learning. We're not interested in the performance in the train set. We are looking at the performance of the model in the test set, something that the model has not seen before. So this means that if I take this green curve and throw the test set at it, so maybe the test set is going to be something like this. And as you can see, the model is going to be way off in the test set. And for that reason, the RMSE in the test set is going to increase. So in general, we see a kind of U shape or elbow shape when you're plotting the RMSE of the test set with respect to the complexity of the polynomial regression model. And the optimal value of polynomial degree, or the optimal value of hyperparameter, is going to be wherever it's going to minimize the RMSE. So here in this simple example, the answer was 3. So we know that this, when hyperparameter, the optimal version is 3, we get a best combination of model bias and model variance, right? So this is RMSE of the test set with respect to degree of polynomial. If I ask you, can you plot the RMSE in the train set, what's your guess? Yeah, in the train set, the RMSE is going to always decrease, right? As you make the model more complex, it's the RMSE in the train set is going to shrink. So that's why we don't focus on RMSE of the train set using machine learning model, right? We focus on something that the model has not seen before. So this is the RMSE calculating in a test set. We also report RMSE in the cross-validation version, cross-validated data. So you may see RMSE cross-validation. And if you watch the video that I covered the cross-validation concept, we said that we do it for 2 reasons, right? First, we use cross-validation for tuning the hyperparameter, so this is the application. And second, we want to make sure that we are looking at the performance of the model in something that the model has not seen before, right? So by this way, we are somehow estimating what is the performance metric of a model in the test set. So it's going to be somewhere in between, not necessarily below the test or above the test, but it's going to be very close to the behavior of the RMSE of the test set. So this is our RMSE in the cross-validation. So in practice, we use RMSE cross-validation when you want to tune the hyperparameters. And we're gonna see a plot like this again and again for every single model that we cover in this machine learning conceptual course. So in short, this we are going to use cross-validation to tune the hyperparameter. And by tuning the hyperparameter, the model is trying to avoid overfitting, get a best combination of model bias and model variance. So here the model is underfitting, here the model is overfitting, and here we know that it's a right fit, right? So let's say it's a perfect fit. Perfect fit. Okay. All right. Now let's talk about the caveats of polynomial regression model and conclude this section. Okay, so imagine this is our data. We're looking at wage versus age, And at the end of the day, you want to predict what's the wage of an individual based on their age. And it seems that there's a nonlinear relationship in the data by looking at these observations, right? The gray circles. And so what are the caveats of polynomial regression model? In general, quadratic loss functions are sensitive to outliers. Remember, guys, both in linear regression and in polynomial regression, our loss function was quadratic, right? We were looking at minimizing the MSE, minimizing the summation of, or the average of that, y minus y hat to the power of 2. Now, if you have outliers, then these errors are going to be large. And then we're going to even make that effect even worse by scoring it, right? So in general, quadratic loss functions, which we have in polynomial model, are sensitive to outliers. So this is something that we should be careful. So if I have outliers here and there, then we know that the loss function is going to be sensitive to those outliers. So that's number one. Number two, polynomials have notorious tail behavior. So what do we mean by that? So this basically, look at this example. Imagine this is a polynomial model with, I don't know, maybe the degree of polynomial is 7. Okay. And if in the tails we have some observations, like, you know, we have a bunch of observations here that are pulling up the entire regression, so maybe here, and we have a bunch of observations down here, which is pulling the entire regression down, right? Look at that. The behavior of the model at the tails are kind of weird, right? So for example, what's the story here? So as age increases, your wage is going to increase, and as age increases even more, the wage is going to decrease. But can you explain this part? It goes up and then comes down. So this is also another caveat of polynomial regression model, because again, they have usually notorious tail behavior, especially if the models are unnecessarily complex. And the third one is that polynomial models are global fit. So what does that mean? So let me erase this extra stuff here. Look at the entire data set, right? So these circles are the entire data set. Polynomial model is going to find a global fit for the entire data set. So it says that, okay, this is the entire data set. Let me for example decrease the degree of polynomial. Let's say degree is equal to 2. Let's use actually green. Degree is equal to 2. If I fit a polynomial, it's going to give me something like this, right? So this fit, or maybe even lower than that. But anyways, the idea is that this fit is a global fit, right? It's not going to split the data into different sections based on different values of age, right? So let me tell you what I mean by that. So the idea is that maybe you want to look at the effect of age on wage when age is between, I don't know, 24, 25, right after graduation, and then maybe 65, right before retirement. So you want to use a fit here. Let's say split the data into 3 sections: when age is less than 25, when age is greater than 65, and when age is between 25 and 65, right? So if I do something like this, if I split the data in 3 sections, so I can use different fits, right? So here I can use a fit like this, here I can use a fit like this, and this is what we call piecewise polynomial, or splines and local regressions, right? But polynomial itself, as we discussed earlier, it's a global fit. It's going to be something like this. And not always, but sometimes it is not necessarily the best model, right? Because we know that if we know the characteristic of the data, if I can split it in this example into 3 parts, 3 meaningful parts, then by fitting different regression lines to each specific part of the data, I may end up with a better model, which usually that's the case. But we know if you use polynomial model, it's going to be a global fit. Okay, so we're not going to talk about piecewise polynomials or splines or local regressions in general in this course, because those are the topics of statistical learning and econometrics. But here in this course, we will be focusing on machine learning methods. As I said in the very first part of this course, in machine learning in general, we are more interested in predictability of the model rather than interpretability. Okay, so for that reason, we're going to avoid this kind of conversation for this course. All right, until the next video, take care. See you then. All right, that's it. This was our module number 5, linear regression, the machine learning approach. So hopefully at the end of this video, you get a good sense of what do we mean by econometric approach versus machine learning approach. So in the next module, we're going to talk about our penalized regressions. Specifically, we will cover ridge regression, lasso, and elastic net. Until the next one, take care.